Good.
Oh, that's fantastic. That's excellent news. Okay, so what we're going to do today is, let me pause this. I really hate technology. I really, I really just want to wipe all the technology off of the entire planet. I'll be very, very happy. It's fantastic. I have no problem studying technology. I just never want to use that. Okay. So we're doing, let me just do a little preamble here. So we're doing static equilibrium. You can call it also equilibrium statics. The question you're going to ask is, what does it mean if an object is in static equilibrium? Okay, so I'll ask you, if an object's in static equilibrium, what does it mean? If you tell me what the it is, I'll agree with you. Not necessarily. That's subtle. How can something actually, hold off on that and we'll come back to that. Yes.
Forces acting on the objects are they all go
Okay.
equal to 0.
So you can say the net forces on something have to equal 0. Now, this means that what's equal to 0 as well? This means that the acceleration is 0. Does that mean the velocity is 0?
Not necessarily.
Not necessarily. You could have v equal a constant. Okay. So this means that A is 0. Therefore, V is a constant. When you take the second semester of general physics, you're going to get this a lot. We can have V equals a constant. And that means that A equals 0, which means that the net force is equal to 0 as well. So you're going to see that a lot. Now, here's the tricky thing. It turns out you need one more thing. And this is why I have a ruler. Okay, so let's take this ruler here. Let's say I'm going to pull up on this with a force F and pull down this with a force F. So in other words, I'm going to do this to my ruler. I'm going to pull up here and pull down there. So I'm going to pull up with a force F. This is the force minus F. Is the net force equal to 0?
No.
Yes. Right? The net force. Is this force? What's this force? Is equal to 0. So the net force is equal to 0. However, will that still be moving?
Yeah. It's still
Yeah, what would happen if I pull up on this end and then pull down here?
Rotate.
And what's that called?
rotation. Angular motion.
Sure. Well,
Dynamic.
think about what were we doing in class? Torque. This is a torque on it. Okay. So in a case like this, these forces might add together to be 0, but you can still have a torque. So you also have to have, so in order for the object to be in equilibrium, two conditions must apply. First, that the net force equals 0. Second, is that the net torque is 0. If you have both of these conditions, you have equilibrium. That makes sense? Okay, the theory is done. That's it. All we're going to do now is problems. For those of you who are mechanical engineers, you'll find out really kind of efficient ways of doing this. Looking at free body diagrams and stuff like this, and there's whole ways of analyzing it. In physics, you don't do a lot with this. In physics, you write this down and say, okay, done, next topic. The engineers will have to, when you make your bridge, it turns out people really don't want to be on a bridge that's moving. That really kind of makes them pretty nervous. So you don't want that moving bridge. Okay, this bridge is moving. Okay. Yeah, let's not drive across it.
we say?
That's perfectly fine. So In physics, we don't do a lot with this, but the engineers do. So let's see how you do this. So here's a wall. This is a beam. Actually, I'm going to show. This is a beam. Let's say a uniform beam. This is a cable. This is a sign. So maybe this is something on in front of a store. Maybe this is, food or something like this. So this is some sort of thing like this. We want to do a couple of things here. What might you want to find for this? You might want to find the tension in the cable. And you also might want to find the force that the wall exerts on this rod here. So let's ask what? Let's say find the tension in the cable. And the X and Y forces. That the wall exerts on the beam. We did an angle here. Let's say that this is 30 degrees. We need some masses of the sign. Let's say the mass of the sign is, well, let's say 20 kilograms. Let's say the mass of the beam. Let's say the mass of the beam is, let's say 30 kilograms. And let's say the length of this here, the length of this pole here, the L. Oh, let's say it's 10 meters. I'm just making these values up. Okay, proceed. You tell me what to do, and I'll give you a hint, your puzzle. Okay, let's do the free body diagram of the sign. What are all the forces on the sign?
Energy going down, tension going up.
That's it.
Your coordinate system is going to be normal x and y.
Okay, you have the normal x and y. When you do all this, what is the sign not doing? It's not moving, so what do you know about this tension? It has to equal this. Okay? Does that help us find the tension in the cable? No. But it's still true.
What you
Okay?
have to do with the beam.
Yes. We're going to look at the free body diagram of the beam. Why would you know the beam? What are we trying to find? The force in the cable and the X and Y force from this wall. And what are they acting on? Well, they're acting on this beam. So you're going to draw the free body diagram of the beam. Okay. What are the forces acting on the beam?
Energy
The weight.
going down.
Which way? It's two.
Mass of the beam going down and the mass of the sign.
Okay, so we have the, now it's going to be important. You have to put the forces where they apply. So the weight from this tension here is actually equal to the weight. So I'm just going to call the weight of the sign. That's acting right here. So I'm going to put that here. So this would be the mass of the sign times 2. Put the force where it applies. Now, we said it was a uniform beam. So where would be the weight from the beam? Center mass of it. So the center mass of this beam is going to be at the center because it's uniform. And so that's going to act right at the center. So this will be the mass of the beam. times 2. I changed my notation. That doesn't look very subscripted. and that's not B. I call that G. I know that because I've studied G and I've studied B. And it turns out that's not G. That's good to know.
There's the tension of the.
How does that go?
It's at the other end.
It's at the tip here, and the tensions are always directed along the cable connecting the two of the string. This would be some sort of cable. So this would be the tension here. Now, this can't be the only forces acting on this. How come?
We're gonna flip the beam.
Yeah, then basically there'd be a force going up, something like this, or this whole thing would go like this.
And normal force from the wall.
Okay, so we could call it normal force, and it is. Okay, I'm not gonna call it that. I'm gonna call it the X and Y components of the force of the wall. Now, how did they have to go? If you don't know, what are you gonna do? Always assume positive values and then let the sign determine what they are. So I'm gonna say that that force from the wall here is gonna be something like this. This would be the force from the wall. Maybe it's not, I don't know. But there's gonna be then some Y force here. This would be the Y force from the wall. And then this right here, this would be the X force from the wall. There are all the forces acting on this. Does that make sense? Okay, so now what I have to do is apply, then what do we know for equilibrium? We have to know that the net forces equals 0. So how many equations are there here? 2, 1 for X, 1 for Y. We're gonna have that condition, and then what's the other one?
Net torque equals 0.
Yeah, the net torque equals 0. Okay. So the trick here is going to be applying this correctly. Because if you apply this correctly, life is going to be quite good. Let's set up these equations first.
We are doing coordinate system.
Hold off on that, but yes, okay. Okay, we'll actually do it right now. Okay, so since we're doing X and Y. Okay, so what is the coordinate system?
X and Y.
Just gonna be standard X and Y. Which way should be positive? That would be fine. What else could we have? Right, why does it not matter?
It's not moving at all, so. it doesn't matter.
It's not moving, but I heard down from Shane first, so we're gonna take down to be positive. Now what about this way? Which way?
Right.
Okay. I think this is positive. That doesn't matter because it's not moving, so you can pick whatever way you want. Okay. So what are the net forces in the X direction?
You've got,
X wall.
This guy?
and then you've got TX, or are you have?
Yeah, what are we gonna have to do with our friend T?
You have to break that out.
Yeah, we're gonna drop it a little perpendicular here. We have this TX here, and I have this TY. This is theta. Okay, so what does that tell us? If the object isn't moving this way,
Oh,
It's
the-
negative.
force from the wall has to, X force from the wall has to equal
The X force from the tension.
next force from the tension. Okay, so this equation gives us the X force from the wall, the X force from the tension equals the X force from the wall. Does that make sense? Tell me about the Y.
You're gonna have F wall Y and TY plus MG, or well, minus MG. No, plus MG because it's going down, and you have the weight of sign.
Okay, so tell me what to write. Everything you said is true. Now just make it.
It's gonna be MVG plus MSG minus F wall Y minus TY
Equals.
equals 0.
Okay, so what does that mean? The forces going up have to equal.
Force is going down.
The forces going down. What forces are going up? This guy and they have to equal this guy and this guy. So put a little box around here. Don't know what to do, put a box around it, it'll make you feel happy. You put a box around it, so there's a sense of finality there. Okay, so the force is going up. about that at all. F equal to forces going down. Okay. Now, we don't know the T, we don't know Fy, and we don't know Fx. There's 3 unknowns and 2 equations. How do we get our third equation? The torque. Now, just let's do a little review here. What is the torque from any one force is equal to what?
I also.
That'd be the total. No. Just the torque is R F or across F. So recall. Torque is R cross F. Where does R go from? The pivot to where the force is applied. Okay. Is this rotating?
No,
No. So where's the pivot?
technically the pivot's gonna be at the end, because if it were to be rotating, the sign would pull it down because it's attached to the wall.
It's actually better than that. Better than that. There isn't one. If it's not rotating, you can pick any pivot you want. I can pick here, 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 here. I can pick any point.
What makes life easiest for us?
Yes. Okay, so what would make life easy? You'd like to take a point where you wipe out a torque.
So the weight of the sign and the part of tension are actually.
Correct. So what you can do here is that if I pick this as a pivot, what's the torque from the wall then? 0, because the R is 0. I could just, this would also be a good choice as well. But I'm gonna pick this one here and life will be good. Okay, so let's take this one here. Does everyone understand the reasoning there? Okay, so I should write that down some more. So since the beam is not rotating, we can choose. Is that what it has, like 2 O's?
Yes.
Yeah. Yeah.
We can choose any pivot point. So choose a point. That eliminates a torque from an unknown force. Okay, so we're going to pick the wall here. So what we're going to do is I'm going to take this to be my pivot. That way, that means that if you look at this force on the wall here, the R for this guy here, the R there is in 0. So there'd be no torque from the wall. So we don't even have to worry about this guy. Okay, so that means that the torque from the wall. So what do we do? What do we do with that torque? The torque is going to come from these things over here. So what do we have? We have the beam. We have the sign. We have the tension. Now, we need some sort of convention. Do we want clockwise or counterclockwise to be positive? A clockwise torque or counterclockwise torque to be positive?
Clockwise.
It doesn't matter, so I heard clockwise first, so we do it. So is this rotating this way or this way? It's not rotating either way. So it doesn't matter which way you take to be positive. So somebody said this one first. So that's what we're gonna pick. Okay. So now let's just go through and calculate all these. Okay, you have these, you can tell me what they are. Okay, so if we look at the net torque, we're going to need the torque from the beam, torque from the sign, and then the torque from the tension. We're going to have to add them together in the unit. The torque from the wall is automatic. physical pivot. So what's the torque from the beam? Again, remember that, we know that torque is all across that. So where's the R go from? For this guy? From here to there. Yeah, so that's gonna be L
What happens?
over 2, right? What angle does this R make with the force? 90. So if we go through and work this out, this guy's gonna be L over 2. M beams G times the sine of 90. Now, is that a clockwise torque or a counterclockwise torque? If this were the pivot, would this cause a clockwise or counterclockwise rotation? And it goes clockwise, so that it is
Positive.
positive. So this is coming on the positive side. Okay, tell me what the force is from the sine.
It would be L because there's all the way over.
Yeah, so from here, the R, so this guy here, that's my R. So this entire length here. So this is L,
MB,
M,
G, 90,
SG,
sine,
sine of 90. Is it a positive torque or a counterclockwise torque?
positive because it's gonna make clockwise.
Clockwise, okay. Now we then have the torque from the tension. So what is that? L, I'll put it down here. So it's going to be plus L T sine of 30 degrees. That makes sense? That sine of 30 degrees, this is just nothing but a T water.
But it's
Right.
gonna be negative L sign because. of the
Correct.
high pressure of the negative.
So this is causing a counterclockwise. This is going to try to cause it to rotate this way. So this is going to come in actually with a minus sign. So it's this plus this plus this. And they have to add together to equal 0. Does that make sense?
Is it supposed to be something in front of the first plus sign in your T
I was just saying plus in this guy here, then I put that guy here. If you want, I can take this guy
Yeah,
out.
about that.
This is just plus.
Yeah, what, is there anything before that?
No.
Okay.
That makes sense? Okay. So now if I solve for this. What do I get? First of all, does anything count? The L. So that's kind of neat. It's independent of the length of the rod there. So the L's cancel. So this gives me MBG. Sine of 90 is 1. I get a half here. Get this guy here. MSG. Take this guy to the other side. And so I'll factor out the G here, divide by sine 30. So this tells me T is 1/2 MB. That's mass of the sine G over the sine of 30 degrees. So this would be 1/2. The mass of the beam was what, 30?
Yes,
Mass of the sine was 20?
yes.
That was 9.8. We are on Earth. Okay. The sine is then 1/2. I just. Okay, you work that out, you get some number. Let's call it star. Now, if you're an engineer, why would you even care about that?
Because the forces don't cancel out, either that sign can go through the air or fall.
That's true. Would something else? But you're gonna use some cable there. What might you look up for the cable?
Tensile strength.
The tensile strength, find out how much you're gonna actually, what it's gonna take to snap that cable. And you wanna make sure that this value is well below any type of tensile strength, because if wind hits it, it's gonna get a little pull on it, that tension can actually fluctuate. And so you'd wanna make certain that there's no way that tension can get even close to that tensile strength. Usually you kind of figure, if you try to over design by a factor of 3. So in other words, you find out what this is here, and you want something probably with the tensile strength, probably 3 times that. That makes sense? Okay, so then how would we then find this? What would be the force from the wall? Why?
Well, you have your T, so you can take the star and put that.
Yeah, so we're going to take this guy here. sorry, TX is what? TX is gonna be the speed cosine of theta. So we get star cosine of 30 degrees to the equal F1. If you're an engineer, why would you care about that value? Why would you care about these forces acting in the next direction on your beam?
You want to make sure that it doesn't go through the wall.
True. Something else too. Forces when you put it on a beam can actually cause them to buckward and it just compress a lot too. You'd want to make sure that basically that beam could actually deal with that type of force, right? That type of force.
So like a strong enough material.
Okay, so then how do you then find the y force? Oh, just gonna crank this out. So the y one. Is this guy? So this would be our 30. I'll pull out the G's. I'll rewrite this as MB plus MSG. And this guy here is then T sine theta. So then this would be our 30 plus 20 and 9.8 star sine 36. That makes sense? That's how you find them. Okay, what would happen if you had the variation like this? Okay, one of the books we had that exact same problem here. But it's great. It had Yogi the Bear here. Hey! The best thing about Yogi is saying, hey! He's saying picketing basket. Picketing basket. Hey, boo boo, hey! That's just so much fun. Okay. So you have Yogi, hey, with the picketing basket. Picketing, right? Picketing basket. Picketing basket. Okay, so you have Yogi here like this. How does this problem change?
Now I have to account for Yogi's weight on the.
Yeah, you have the exact same thing, but now you have to put the torque due to Yogi. And so the question is basically they had some sort of cable strength in the beam. Question is how far could Yogi go before the basket would break?
So you get the basket.
Exactly. Okay, I was at a place before. Okay. The first place I ever taught at was a place in South Carolina, which I was the new guy there. So they gave me all the crappy courses that nobody liked. So I was the new guy there. And they put me in this one course, which made me infinitely patient, which it really did. So they had this, there was this question here, and they had to do it. So you had to find the distance here R, like this. And I said, oh, it's really easy to do. I said, all you have to do is that you have a bear here, divided by beam, right? The BEAs cancel. All we have to do is find the ratio of R over M. And this one kid raised his hand and went, does that always work? I wasn't ready for that. I really, that's just where you can tell like, my heart. What's happening?
Does it always work?
How can it not? This is the same place, and I'm kidding, I'm not making this up. So there's a lab where you had to measure the resistance of a wire. And all you did was show that as the length of the wire increases, the resistance goes up. There was a question in the lab, and these two students even came by to ask me how to do it. They said, what metal would make the best wire for a house? What is it, and why don't we use it? And I'm not kidding, this burned into my synapses, and I never forgot it. You know what the answer is? Blood. Blood makes the best wire for a house. We don't use it because we need it to live. That's verbatim. And so, you know, you read that for the first time. You say, blood. Oh no. And then you read it again, you realize it says the same thing. And you can just feel your brain kind of turning on. And you just kind of go to the refrigerator and you open it up, and you grab a beer. You go back to your bed, and you sit in the bed with your clothes on, sitting up with your beer, and you pull the blankets over your head, and you just stay there. Because it's safe. Because you're inside, you're under your covers, and you have your little beer, and you're in a little tight ball, and it's safe. That,
But you're in your house that could be made of wood.
it's, but it's safe. That's,
How would you even use?
I
Blood
don't,
is a wood.
I don't,
I mean, blood has iron in it, yes, so
I-
is it iron?
I don't know, but they said blood. That's, I just know they said blood. And that was exactly what they said in this thing, and it's just one of those things like, oh no.
I don't know what these kids are doing with their lives now.
Okay, let's try another one.
I wonder if they graduate.
How they get in college?
I honestly don't.
Or they have their own employer engineers.
Okay, so let's say here's this. Let's say this is 60 degrees. This is a ladder. This one here, the wall's gonna be frictionless. Okay, wall will be frictionless, the floor will not be. Floor has friction. Say this is some L here. What's a good ladder length? 3 meters?
7 years.
7? That's a really, yeah, you could do that one. Let's say 7 meters, 60 degrees there. What's a good ladder mass? Let's say 50 kilograms. Okay. Let's find the force on the wall here and the force on the floor here. On the force. This doesn't move. Ladder doesn't move. Okay, so find the force at the wall and floor. Exert on the ladder. You tell me what to do. What kind of problem is it? What would be the indication of this? Why would you not do a free body diagram? That's completely correct. When you're hearing force words, you think free body diagram. Okay, anything like acceleration, force words, you think free body diagram. Okay. There. What are all the forces acting on?
There's the mass of the ladder going down to the center of mass.
Yeah, we're showing a uniform ladder, so you're gonna have the weight acting right at the very center this time. That'd be the mass of the ladder. I'll just go M function. Yes.
Would there be 2 normals because there's 2 points of contact?
Okay, if you tell me where they are, so you're gonna have one here and one down here as well. That's right. You're gonna have this force, this will be the force from the wall. This is really gonna be the normal for the wall. Okay. And there also is one from the floor like this. So this would be the force. This would be Y force from the floor, which is gonna be the normal from the floor.
You have to worry about the X component of the floor.
Okay, now why can't there be the only forces on this thing? If you only have this object too. Yeah, it's start moving and go this way. That doesn't happen. Okay, so there's friction on the floor.
There's also the walls frictionless.
Yep, we're gonna get back to that point. So what else do you have then? Yeah, there's gonna be friction on the floor going this way. So this would be the floor here, the X direction, and this is really just gonna be your friction. What kind of friction is that gonna be?
Static.
That'll be static friction. Now, if there had been friction on the wall, we're not gonna deal with this. So if there had been friction on the wall, what else would you have?
You have force of friction. Why do we look at this?
How would this thing move? if it's starting to slope.
It starts to go
It's
that way.
starting going like this. So what is, how the friction go? It has to be going up like that. We'll just deal with this one here. So they're all, that's not looking good. No, that's not. Okay, so they're all the forces that we have on this. Does that make sense? Christine. F naught. F naught what? Z equals 0, okay? So that means they're not force in the x direction. 0. Not force in the y direction. And torque. Okay, and you just can't torque about it. You really have to write it out. Okay, so you're not torque. Okay. Proceed.
Yes, all the forces basically in the S direction. So that would be,
So what does this guy give you? If the object isn't moving this way.
oh, wait, where does this just establish?
Okay, okay, this will be y and this will be x. It's not moving, so it's not gonna matter which way it's
Just
positive.
do right now.
Okay. If it isn't moving this way, what can you conclude? Yes.
So you just have to make all the x forces equal each other and all the y forces equal each other.
Exactly.
essentially.
So what does this give you then? If this guy here has to equal
Force on the floor.
the static frictional force, and this guy here has to equal this is going up. So the forces going to the right have to equal the forces going to the left. So this guy gives you this guy gives you this static frictional force here going this way. That's equal to this force from the wall this way. I'll just because that's what it is. Okay. Then what does the y equation give you? It gives you that this has to equal this. Understand? Okay. We need to pivot, right? So now we have to do our torque. I take the bottom as well. How come? Yeah, I can go 2. Okay. I could just as well do it here, and I could do this, but then it's going to be more cumbersome. Okay. So I'm going to choose this to be the pivot. Take it as the pivot. I want to show you a variation you can do on this stuff here. So let's do this. I want to go back to. You can tell me what the values are for this guy. I want to do a little recall. And when we do this torque, if here's our pivot, here's our force. We call this R. What can we do with that force? We break it up into parallel to F, I mean R, and perpendicular. Right, we call this theta. We say the magnitude of the torque is this magnitude of R times this F perpendicular. What is F perpendicular? Magnitude of F sine of theta. I can do something weird here. I can take this R and put it with F. I'm sorry, take this R and put it with the sine. I can look at this. So instead of taking F and breaking it up into part parallel to F, instead of taking F and breaking it up into part parallel to R and perpendicular to R, I can take R and do what with it?
Break it up into its own components.
Parallel and perpendicular to what?
F.
To theta.
So what I can do is complain about limited blackboard space in this next one, but I'll put it over time.
But you're not limited, it's just that the camera limits.
Yeah, I know, but I still like to complain about it. It still makes me feel happy whenever I complain about it. Just feel more satisfied about myself. I needed these equations 100%. So what you could also just as well do That's one. But here's your F. R. I can go like this. I can call this R perpendicular and call this R parallel. So this is a part of R that's perpendicular to F. The part of R here that's parallel to F. This is theta here. So this R perpendicular. R. You could say, well, thanks, that's useful. It is. In this case here, here's my R and here's my F. If this is R, what would be R perpendicular in the picture? I can say the torque from this wall as well.
R parallel?
I can take this R here
No.
and break it up into part like this and like this. So I can say the torque through to this guy is going to be this distance here. And times this. So I can say, this is a very subtle point. So when I have this guy, here's my pivot, here's my R, here's my F, all X. I can break this up like this, like this. So here's my kind of R perpendicular, and here's my R parallel. And this is theta here. So I can say that this R perpendicular is this R. I'm just sign of theta here like this. So I can say the torque due to the wall force is going to be, when I work this out, you can say it's going to be this guy here, R perpendicular, and this guy here. So this is going to be my R. This case here, this R here, the magnitude of it is L. So this is L sine of theta. And this wall force. Very subtle. Make sense? So let's say I should go through and put them all in. You don't have to do it this way. If you want, I can take this force, I can break it up like this, and like this, and then calculate this guy here as well. That's just as fine. It's easier to probably drop the perpendicular like this. Take this guy. If I look at the net force here, net torque, it's up to 0. You have the torque from the wall here, plus the torque from the weight. After you add together to equal 0. So if I take this as a pivot, I'm going to have a torque from here, and then a torque from here. So the torque from the wall force, and which way is positive?
Doesn't matter, because it's
So
not
give me a direction.
counterclockwise.
Counterclockwise. So we're going to take that to be positive for no good reason. So this be a positive torque or negative torque? That'd be a negative torque. So this would be minus my friend over here. Plus, now what's the torque due to my friend here?
Positive.
Positive and given by what?
G.
One more time. L over 2. So you need the L over 2 sine of theta. This is my R perpendicular. Then times your, actually no. Was your R perpendicular in that case? This is my R. And this guy here, which is
G cosine.
yeah, this would be L over 2. Cosine of 60. Okay. G. Pretty slow.
Do the L's cancel out in this?
Yes, I do. This gives you F the wall. Is your 1/2 mg cosine 60. If you look on your practice thingy,
We wanted to, we turn that into a prime tangent.
you could, I want to put that in front. So I'd write this as 1/2 mg or 18.60. Trig is your friend.
Is it acceptable or F1? It's the theory of
No,
F.
that's, because I'm sloppy, thank you. Keep me honest. Okay. Then you then how would you then find the F for the 4 here? You know that this right here would have to be, this guy here has to equal that guy here. That would give you this one. And then, you know that this normal force then has to equal the weight. That's just room to tap it all. Does that make sense? That's kind of a simple problem. Now, if you look at the practice thing I gave you. What would you do with one like this, number 6?
It's just like the first couple of it.
Oh, I'm sorry. Oh, I'm sorry. I had to define T. Why did you do that?
Start off with a 3 body down the road.
Yes. Yep. Does the beam have mass or doesn't it?
It's all mass plus by radius.
Okay. So what are all the forces acting in the beam?
Mg sine going straight down on the right.
Okay, so this guy, so this is the mass of the sine or whatever the thing is.
And you have the mass of the beam from the center of it going down.
Assuming a uniform beam.
Are we ever going to do a problem where it's not a uniform beam?
You have the force and tension going up and right above the MSG.
What's the wall?
How does that go? I have no idea, just draw something so that the components are always constant. They're gonna say this is a force from the hinge. Apparently called the fin. I'm kidding, or I'm fitting. Okay. So this is your force of the hinge X, force of the hinge Y. Proceed.
X net equals 0, F y net equals 0. Or net torque equals 0.
Why do you know this? Because
It's not moving.
that beam isn't moving. Okay, so this is an equilibrium, static equilibrium, equilibrium. It's one of those names. Okay, one of these is going to give us the answer immediately. Which one? Oh,
Net torque.
why is the torque going to give us the answer immediately?
Because the tension is equal to the mass of the sine times the gravity.
Everyone agree?
Yes.
Can you tell me why that doesn't work? Okay. These two don't necessarily equal each other. What equals each other? All the forces going up equaling all the forces going down. You have to look at the entire thing.
So tension plus F hinge Y equals MVG plus MSG.
Yeah, so this force, the Y component of the hinge force, plus the tension has to equal this plus this.
Can we always assume that Y is going to be going up and X is going to be going that way?
Yeah, we're just gonna take the standard. Okay. Now, the problem with this is, we don't know T and we don't know this guy. So why does it claim that this guy's gonna basically allow us to do everything?
Because there's some physics magic that does something.
If we take the pivot point at the top, we can eliminate.
Exactly. If we take the pivot here, what's the torque then from the hinge?
Zero.
It's 0. That allows us to basically eliminate that whole contribution. We're gonna take this to be the pivot. Okay. So if we do that, what do we get?
So that torque is gonna equal torque of the pivot, which is 0 plus the torque of.
So we said the torque of the, also the torque of the hinge. Plus
Torque of the beam,
the beam,
torque of tension.
torque of the tension.
Did you include, does the sine give off torque?
Can't wait to find out.
I'm gonna say yes, it does.
Yes, it does. They have to all together equal 0. Okay, so the torque from the hinge is equal to 0 because that's where we've taken this, the right? So this is 0. So what do we get? We get the torque of the beam. Tension. Okay. Let's figure out what these are. Which way do you want to be a positive torque? A counterclockwise rotation or counterclockwise?
Clockwise.
Clockwise. Does it matter? No, just as long as you're consistent. Okay, so what's the torque from our sine here? Again, I can take this weight and I can break it up into a part just like this and like that. Which of these components cause it to rotate? This perpendicular component here causes it to rotate. So what is that going to equal?
SG.
Actually, we need some things here. Okay, so what is
Well, where is that?
what is this angle right here?
Would that be 15?
Yeah, can't wait to find out.
90 minus 15.
Yeah, this angle here has to be what? Yeah, it has to be 180, because right, if you add these all together, you get 180. So it's 180 minus 90 minus 15, which is 90 minus 15, which is 75. Okay, so 75. Okay. So what we have? This is 75, this is 75. Okay. So what do I have then for the torque of the beam?
And you do the sines of-
I take the L here,
L2.
L over 2. I'm saying this whole thing has length here. That's L over 2. Then I need this perpendicular component here, cause rotation.
MVG sine 75.
Is that a positive torque or negative torque?
It's gonna be positive, because you find that force, it's going clockwise.
Yeah, that'll cause a clockwise rotation. Okay, let's put in the sign. The SIGN sign.
LMSG times sine of 75.
So it's going to be the R, MS, sine of 75, because again, what we're doing here is I can take this guy here and I can break it up. And this component here, just like this. This is your theta. This is the component causing the rotation. Notice I could just as well have taken this here and then taken this L over 2, broken it up into a perpendicular part, a parallel part, and gotten the same answer. That would also work just as well.
Since we know that the torque of the tension is gonna be negative, so we just put that equals and then we figure out the tension.
Yeah, you can, once we get this guy in here. You have to write the expression. No, like, don't skip too many steps, so, because it's easy to make mistakes. Okay, so tell me what then okay, so this is a sine guy we did. Now tell me about the torque from the tension.
It's gonna be minus.
Yeah, this is causing a rotation this way. So I can take this tension here. And this is their 75 here. So I can drop me a little perpendicular. Here's my parallel part. Here's my perpendicular part. This is the component causing the rotation. So what am I going to have? You tell me what direction.
Minus
Minus.
LMSG sine.
Okay, what's the force? T. Then sine of 75. Equals 0. Okay, what cancels?
L's. Yes, L's.
All the L's and all the signs. Okay. We get MBG over 2 plus MSG. Get my friend here to the other side. We go 2. That's what we got. Questions? That's all I can do. That's, these are not hard problems to do. Sometimes there's some couple of little ankle things. Again, there'll be enough questions on there that you don't even have to do this on the final. I will give you a couple of these. I will not give you anything overly dramatic. I'm not gonna give you something where it's like
Similar to these. but-
similar to these. I would not give you something like this because there's enough angles. I give you something a little more straightforward. Okay? So tomorrow if you come, it'll be angle momentum. And we'll figure out the very beginning of any James Bond movie. Okay, what's the very, very beginning of any James Bond movie?
When that camera one shoots him and blood rains down.
You see this. This. What is that?
Inside.
It's a rifle.
It's a rifling.
It's a rifle. Okay, you're looking through the rifling of a gun like this. It's not a camera, it's a rifle. And how do we know it's a rifle?
Because the lines.
Because of these lines here. So the question is, why does a rifle have these? For a very good reason. And we'll see why. Yes.
I know them, it's because
I mean,
they.
doesn't have to be a rifle.
Yeah, it's gonna spin the ball for a reason.
Yeah.
Is rifle the only one that has those or the one I just meant the house?
Well, I mean, like a shotgun goes, like that. But a rifle you want to be at. The shotgun you just have to be.
I mean, well,
They're talking about that because they're talking about the American Revolution and how they designed it somehow that eventually will be going astray.
Eventually, I mean, okay, wars drive a lot of things. So at some point you want more accurate bullets. And so then you start doing things.
if you're like me and you have 5-year-olds challenging you to hit a birdie, you gotta be pretty accurate.
Have a good day.
I forgot to come up to you for class.
Sure.
It's really not that big of a
Okay.
deal. There was just like a math error
Okay,
adding up
sure.
all of my points on this.
That's